In this example, our differential equation is 9x squared y double prime plus 9x squared y prime plus 2y is equal to 0. We can see that from the x squared y double prime term, x equals 0 is a singular point, and further, it is a regular singular point. I want to start by finding the indicial roots. For that, we need to put the equation into a form where the first term is x squared y double prime. And that, in this case, that means dividing by 9. So we've got x squared y double prime plus x squared y prime plus 2/9 y is equal to 0. Once we have our x squared y double prime term, remember that our y prime term always has the form x lowercase p of x y prime. And then the y term is lowercase q of x times y. Since x p of x y prime is x squared y prime, we know that lowercase p of x is equal to x, which means the constant term a sub 0 is 0. For q of x, we have 2/9, and that gives us that b sub 0 is equal to 2/9. And if you don't know what I'm talking about here, you really need to watch the previous video. The indicial equation is r times r minus 1 plus a naught r, so 0r, plus 2/9 is equal to 0. Clearing the fraction and the parentheses gives us 9r squared minus 9r plus 2 is equal to 0. And that factors into 3r minus 1 times 3r minus 2, and then that equals 0. And so we find that r is equal to 1/3 or 2/3. And we'll just note here, these don't differ by an integer. That's all we care about for now. We have our indicial roots. We'll use them later, but what I now need to do is actually go back to the original form for the equation. And I guess I can say everything we just did isn't really necessary for solving the equation, but it's necessary for understanding a particular part of the process, and then it will help to validate something along the way that I'll talk about when we get there. So back to our original equation. I'd like for you to start with y equals the sum as n goes from 0 to infinity of c sub n x to the n plus r, and differentiate, flesh out the differential equation, find the indicial roots, and then come back. And we'll pick it up from there. For 9x squared y double prime, we have the sum as n goes from 0 to infinity of 9 times the quantity n plus r times n plus r minus 1 c sub n x to the n plus r. For 9x squared y prime, we have the sum as n goes from 0 to infinity, 9 times the quantity of n plus r c sub n x to the n plus r plus 1. And for 2y, we just have 2 with our regular expression for y. Making exponents match, that means making them all match n plus r, or I should say k plus r, means the first and third sigmas we don't need to touch except to change n to k. The second sigma, we need to change the exponent there. But for the first two, since they all have, or since they both have c sub n and x to the n plus r, I went ahead and combined those already into one sigma, where k has replaced n. For the second sigma, we're taking that exponent n plus r plus 1, we're going to write it as k plus r, and so the cosmetic change is that we are subtracting 1 everywhere we had an n, and then we offset that by increasing the index by 1. And then to make the indices match, we have 1k equals 0, 1k equals 1. Writing down the k equals 0 term for the first sigma expression gives us 9r times the quantity of r minus 1 plus 2, all times c sub 0 is equal to 0. And you'll find that that gives us indicial roots of 1/3 and 2/3, as we saw before, and that's the check that we're looking for here. Now that we have that, let's look at the sigma expressions. Since we've already written down the k equals 0 term for the first sigma expression, we effectively have two sigmas that have the same starting index and the same power on the variable x. So rather than writing down the sigma expressions, we can just write down what's going to give us the recurrence relations. From the first expression, we have 9 times the quantity of k plus r times k plus r minus 1, all that plus 2, times c sub k, and then plus from the second one, 9 k plus r minus 1, c sub k minus 1, and all of that is equal to 0. And continuing with the strategy that I consistently employ, we're going to solve for the constant that has the largest subscript. In this case, that means we have c sub k is equal to negative 9 times the quantity of k plus r minus 1 divided by 9 times k plus r times k plus r minus 1 plus 2, right? The 9 does not affect the 2 there. Times c sub k minus 1, and that's for values of k from 1, 2, 3, etc., which we get from looking at the sigma expressions above. Earlier we had found that r is equal to 1/3 or r is equal to 2/3. When we substitute the fraction 1/3 in place of r, we get fractions all over the place, but we can use the factors of 9 in order to clear those fractions. And I'll spare you the details, but when all is said and done, we have c sub k is equal to 3k minus 2 divided by k times the quantity of 3k minus 1, c sub k minus 1. That's for r is 1/3. For r is 2/3, we get c sub k is equal to negative 3k minus 1 divided by k times the quantity of 3k plus 1, c sub k minus 1. I would encourage you to confirm that on your own so you can see what that process looks like. For the indicial root k equals 1/3, when k is equal to 1, we get that c1 is equal to negative 1/2 c sub 0. When k is equal to 2, we get c sub 2 is equal to, when all is said and done, 1/5 times c sub 0. For the indicial root r equals 2/3, we have c1 is equal to negative 1/2 c sub 0, and c2 is equal to 5/28 c sub 0, using a simplifying process and substituting process that we've seen in previous examples. When we form our solutions, we need to remember what I'm going to call again the Frobenius thing. Remember, we have this x to the r in our solutions. For the constants that we got from r equals 1/3, I'm going to substitute the c sub 0 and write down c sub 1 is equal to that c sub 0. And for r equals 2/3, I'm going to use c sub 2 in place of c sub 0. That'll separate out our two solutions and give us a general solution of y equals c1 x to the 1/3 times the quantity of 1 minus 1/2 x plus 1/5 x squared, and so on, plus c2 x to the 2/3 times the quantity of 1 minus 1/2 x plus 5/28 x squared, and so on, giving us our two linearly independent solutions of y1 is equal to x to the 1/3 times 1 minus 1/2 x plus 1/5 x squared, and so on. And the second solution, y2, which is x to the 2/3 times the quantity of 1 minus 1/2 x plus 5/28 x squared, and so on.